Hello friends, here we are going to start the new syllabus topic. The chapter is simple stresses and strains. Here the important topic is volumetric strain, then uniaxial, biaxial and triaxial stresses. See, volumetric strain. When a body is subjected to external forces on its face, there will be a change in its volume. The ratio of change in volume to the original volume is known as volumetric strain. It is denoted by EV. So EV is equal to delta V upon V. Here delta V is change in volume and V is the original volume. Here V is equal to length into width into thickness, that is LBT. By partial differentiation, delta V is equal to delta L into in bracket B into T plus delta B is equal to in bracket L into T plus delta T is equal to delta T into LB. So here again I am telling you, by partial differentiation delta, V is equal to delta L in bracket B into T plus delta B in bracket L into T plus delta T in bracket L into B. Here delta V upon V is equal to delta L in bracket B into T plus delta B in bracket L into T bracket complete plus delta T into in bracket L into B bracket complete upon V is equal to L into B into T. So here delta V upon V is equal to delta L upon L plus delta B upon V plus delta T upon T. So EV is equal to EX plus EY plus EZ, because we know that L, B and T are the dimensions you can see in this equation. EV is equal to EX plus EY plus EZ, means delta L upon L is nothing but EX. Delta B upon B is nothing but EY. Delta T upon T is nothing but EZ. The volumetric strain is algebraic sum of all axial or linear strain, that is EV is equal to EX plus EY plus EZ. So EX is nothing but strain in X direction, EY is nothing but strain in Y direction, EZ is equal to strain in Z direction. So here, one more important topic, that is uniaxial loading, biaxial stresses, triaxial loading. So here, just see this diagram. Length is given, width is given, and height, you can see the thickness is also given. So the L, B and T is given. Load is acting on this plane, that is P. You can see that is the load P. You can see the load P is here. Here L is the length of the bar, B is the width of bar, T is the thickness of bar, P is the load applied in X direction. See, this is the P, load applied in X direction. So here stresses in X direction, that is sigma X is equal to P upon area, that is cross sectional area. See, this is your B and height is, or you can say the depth or thickness is T. So area will be B into T. This is your cross sectional area. Stresses in Y and Z direction will be 0. Sigma Y is equal to sigma z is equal to 0. And strains. Strain in x direction is equal to Ex is equal to sigma x upon E. And lateral strain, that is strain in y direction, is equal to Ey is equal to minus mu into linear strain. Means minus mu into Ex is nothing but minus mu into sigma x upon E. That is capital E. Already I explained what is by linear strain, what is in by lateral strain, what is in by Poisson's ratio, that is mu. So according to this, here Ey is equal to minus mu sigma x upon E. And lateral strain in z direction, Ez is equal to minus mu into linear strain. So minus mu into Ex, again there will be a minus mu sigma x upon E. So here volumetric strain in rectangular bar EV is equal to delta V upon V is equal to sigma x plus Ex plus Ey plus Ez. Here we know that Ex is nothing but sigma x upon E minus mu sigma x upon E minus mu sigma x upon E. Here we are taking sigma x upon E is a common, so is equal to sigma x upon E in bracket 1 minus 2 mu, bracket complete. So here sigma x upon E is nothing but Ex. So here E into in bracket 1 minus 2 mu, bracket complete. So here EV is equal to, means volumetric strain is equal to E into in bracket 1 minus 2 mu, bracket complete. This is your case 2 for volumetric strain of a circular bar. So you can see the length of bar is given, the diameter is given, P is acting in the x direction. Again, this is the L length of circular bar, D is the diameter of bar. Let delta L and delta D be the change in length and change in diameter respectively. So we know that original volume of bar V is equal to pi by 4 into D square, that is area, cross-sectional area into L. Change in volume of a bar, that is delta V is equal to pi by 4 in bracket D square into delta L plus 2D into delta D into L by partial differentiation. See here EV, that is volumetric strain, is equal to delta V upon V. So after putting the values, you will get this equation. That is pi by 4 in bracket D square into delta L plus 2D into delta D into L upon pi by 4 into D square into L. So here you will get delta L upon L plus 2 delta D by 2. So is equal to delta L by L is nothing but linear strain, and 2 into delta D by T is nothing but a lateral strain. So EV is equal to, means volumetric strain is equal to E minus 2E lateral. So negative as a lateral strain is in opposite direction. So EV is equal to E minus 2 into mu into E. So again, EV is equal to E into 1 minus 2 mu. So The change in volume of a circular bar delta V is equal to V into E in bracket 1 minus 2 mu. That is for uniaxial condition. Now you can see here for biaxial stresses. Please observe this diagram very carefully. Sigma x is given, sigma y is given, sigma x, that is stress acting along the x-axis, sigma y is given, that is along y-axis. This is the rectangle member having a dimension x, y and z as shown in figure. It is subjected to stresses into two directions, that is sigma x and sigma y, due to forces Fx and Fy acting on it. Sigma x is equal to Fx upon y into z. Sigma y is equal to Fy upon xz. See, because dimensions are x, y and z. So sigma x is equal to Fx upon yz. Sigma y is equal to Fy upon xz. The effect of Fx is to produce tensile strain in x direction and induced compressive strain in the lateral direction, that is y and z direction. Similarly, in the effect of Fy is to produce tensile stress in y direction and to induce compressive strain in x and z direction. Because here you can see sigma x, this one is a sigma y. The y direction, that is sigma y, the x direction, that is sigma x. So here you can see Ex is equal to delta x upon x. So the tensile strain due to Fx in a linear direction minus compressive strain due to Fy in lateral direction. So the formula will be Ex is equal to delta x upon x is equal to sigma x upon E minus mu into sigma y upon E. Ey is equal to delta y upon y. That is very important thing. Tensile strain due to Fy in a linear direction minus compressive strain due to Fx in lateral direction. So here sigma y upon E minus mu into sigma x upon E. And Ez is equal to minus mu sigma x upon E minus mu sigma y upon E. So Ev is equal to sigma x plus sigma c. Ev is equal to Ex plus Ey plus Ez. You can see in this diagram. We have the value of Ex, Ey and Ez. Just you have to put all the values instead of Ex, Ey and Ez. Whenever you will put all the values in this equation and you will simplify this equation, you will get Ev is equal to sigma x plus sigma y upon E in bracket 1 minus 2 mu. That is for biaxial condition. Tensile stresses are considered to be positive and compressive stresses are considered to be negative. That is important note. So you can see here Ev is equal to sigma x plus sigma y upon E 1 minus 2 mu in the case of biaxial. In the case of Uniaxial EV is equal to E into 1 minus 2 mu. Now, the another point, that is volumetric strain for triaxial loading. You can see the dimensions. X, this is your Z, and this is a vertical Y. Here, Fx is given, Fy is given, and Fz is given. You can see here, this is your X axis, this one is your Y axis, and this one is your Z axis. The rectangular plate is shown in the diagram. So we know that triaxial loading, the diagram shown in the 3D state. The body is said to be under triaxial loading when it is subjected to three loads, which are mutually perpendicular in the direction, say X, Y, and Z direction. You can see that this is your X direction, this is your Y direction, and this one is the Z direction. See X, Y, and Z. Consider a rectangular specimen subjected to three tensile stresses which are mutually perpendicular to each other as shown in figure. You can refer this figure. Let sigma x, sigma y, and sigma z be the stresses in three directions. So sigma x is equal to fx upon yz, sigma y is equal to fy upon xz, sigma z is equal to fz upon xy. Strain in x direction. Ex is equal to sigma x upon E minus mu sigma y upon E minus mu sigma z upon E is equal to 1 upon E in bracket sigma x minus mu into sigma y plus sigma z. You can see the equation number 1. Whenever strain in y direction, there will be a Ey is equal to sigma y upon E minus mu into sigma x upon E minus mu into sigma z upon E. So here formula will be 1 upon E in bracket sigma y minus mu into in bracket sigma x plus sigma z bracket complete into whole bracket complete. That is equation number 2. Whenever you will consider strain in z direction, that is Ez is equal to sigma z upon E minus mu into sigma x upon E minus mu into sigma y upon E. So is equal to 1 upon E in bracket sigma z minus mu into in bracket sigma x plus sigma y bracket complete whole bracket complete. That is equation number 3. You can see here while putting the value of Ex here sigma x upon E, while putting Ey here sigma y upon E, here putting Ez sigma z upon E. So for Ex, for Ey, and for Ez, these are the conditions. While taking X, the remaining two terms likewise, Y and Z. While taking Y, these two terms as a X and Z. While taking Z, these two terms like X and Y. See, this is your equation number 1, this is your equation number 2, and this one is your equation number 3. Strain in X direction, strain in Y direction, and strain in Z direction. So the volumetric strain is equal to EV is equal to EX plus EY plus EZ. Now we have all the values. After putting all the values, means from equation number 1, from equation number 2, and from equation number 3. Here the formula will be delta V upon V is equal to 1 upon E in bracket sigma x plus sigma y plus sigma z bracket complete into 1 into in bracket 1 minus 2 mu. That is equation number 4. So these are the very important formulas. Please note down these formulas very carefully. EV is equal to delta V upon V. EV is equal to delta V upon V. EV is equal to delta V upon V. But for uniaxial loading, the formula is sigma x upon E in bracket 1 minus 2 mu bracket complete. Here for the biaxial loading, 1 minus E in bracket sigma x plus y bracket complete into in bracket 1 minus 2 mu bracket complete. For a rectangular section, triaxial loading, the formula will be sigma x plus sigma y plus sigma z upon E 1 minus 2 mu. See, generalized Hookes law. You can see this diagram. That is sigma x, this one is sigma y, this one is sigma z. Cube is given, so all the dimensions A, length, width, height. So here Ex, Ey, and Ez is given. That already we know how Ex for two directional stress system. This is Ex, Ey, and Ez. For dimensional, three direction stress system, Ex, Ey, and Ez is given. This is generalized Hookes law. Please highlight each and every point. In the next video, we will see the elastic constants like Young's modulus, bulk modulus, or you can say the modulus of rigidity and relationship between them. Thank you. Thank you very much.